When it comes to graphing motion, one of the first things we're going to take a look at is what's known as a position time graph. And a position time graph, quite simply, just plots an object's position, or where it's located in space, over a given amount of time. So this would be an example here. So as time goes by, their position is changing here. In this section, as time goes by, there is no change. The value for position is not changing, so we can conclude that the object is not moving. So these are some of the basic pieces of information you can get from a position time graph, even if it's as simple as, well, it's moving away from where it started, it's not moving at all. There's plenty of information. The more specific information we can get, and what we're going to look at in this video, are four specific things. Just using a graph, how could I determine the distance an object has traveled, as well as the displacement it's experienced? And also, how can I get the speed as well as the velocity from one of these graphs? And if you take a look, there's not much here in terms of numbers. You just have a graph and a line, and with that information alone, you're able to get all four of these, which is fairly impressive. So graphing motion and graphical analysis of motion tends to be more powerful than just simply being given numbers. Because if you're given the numbers, you're limited to analyzing that specific point in time. The graph provides information of the entire motion, so you can analyze segments, you can analyze the whole thing as an average overall. You can get much more specific, much more general, and we're going to take a look at how to find these four things in this video. So that would be the goal. So we'll start with the distance. So what I've done here is I've drawn just a position time graph, and I want to point out here that the x-axis is where the position of the object is 0. Anywhere on the x-axis, its position is 0, and that would just represent where it started. So one kind of key concept to get used to about these position time graphs are that the x-axis is the object's, to be fair, I shouldn't say starting location. I'll say starting location here because this is where it started. This will be our reference point, so it's better to say this is my reference. Because the object certainly could have started like 3 meters in front of my reference point, or 4, and we'll see situations like this. So I would call this a reference point instead. So if you're taking notes, I would call this the reference point rather than the starting location. I've broken this motion into two segments because clearly there's two different things happening here. I've called 1A and 1B. Hopefully, you can see from some of the lab activities and some of our discussions that for the first 4 seconds, the object is moving away from where it started. That's why its position value is growing. Okay? At that point, that value then goes from 4 to 3 to 2 to 1 and essentially back to 0. So during this section, the object was actually moving back towards where it started. If we want to determine the distance, that's the easiest part. You simply just read the graph and you add up the distances the object has traveled. So for leg A or section A, I've gone 4 meters. For section B, I've gone from 4 down to 0, which is also 4. So for section A, I've gone 4 meters. Granted, it was 4 meters forward, and B was 4 meters backwards, but distance doesn't care about direction. So the total distance that I've traveled, or this object has traveled, is 8 meters. It took them 12 seconds to do so. They went forward and backwards, but just determining distance, 4 meters forward, 4 meters backwards. Distance tends to be the easiest to get from these types of graphs. In terms of displacement, it's a very similar concept. You're still reading the graph. However, this time you have to account for direction. I'm going to go over 2 examples here just to show you what I mean by that and how the distance and the displacement readings from a graph will differ. Again, I should really call this a reference point. So this is my reference point. It happens to be the starting location here, but again, the object could have started here, 2 meters, 3 meters. It could have started in front of my reference point, but I'm going to go ahead and say this is my reference point, and in this case, it happens to be my starting location. Again, I've broken the motion into the 2 segments that we see here, A and B. In both cases, the object is moving away, but it's moving away at slightly different rates or slightly different speeds, so to say. If I look at leg A, it took 4 seconds to go 2 meters. So it's going away, I'm going to call it positive 2 meters. So for leg A, it went positive 2 meters, which is the same as saying 2 meters away from where it started. There's that directional component. For B, it started at 2, and it went to 4. So it therefore also went positive 2. It went 2 more meters away. Granted, it's 2 meters away from where it ended at A, and 4 meters overall, but I'm just breaking them down into individual sections. A went positive 2 meters, B went another positive 2 meters. Since they're both in the same direction, and they are both positive, at the end of the day, this object wound up at positive 4 meters, better known as 4 meters away from where it started. I didn't even necessarily have to add these. I could just say, well, I started at 0. I ended at 4, and since displacement only cares about my beginning and ending point, or my beginning and the location I'm currently at, I could have also just read that and said, well, I'm 4 meters away from where I started. To look at a second example where you have a change in direction, this is where the directional component becomes even more important. For section A, I wound up going positive 3 meters, or 3 meters away from where I started. For B, I went from 3 down to 1. So I only went backwards, or negative 2 meters towards where I started. Some people tend to get confused and they think, oh, well, I was at 3, I went down, I must have gone 3. They tend to misread the graph. Just realize I started at 3 and section B ended at 1, so negative 2. If I add those together, I wind up at plus 1 meter, also known as 1 meter away. Or I could have seen that I started at 0, I ended at 1. Doesn't matter what I did in the middle. Displacement just cares about my beginning and my end. So my total in this case at the end would be 1 meter away from where I started. Just as a side note, realize in this case, if I had asked for the distance, the answer would be 5 meters because we would ignore these directional components and we would just add 3 and 2. So this is where the displacement and the distance start to differ. Okay, so direction becomes very important. You have to keep in mind whether the object is moving away from where it started or back towards where it started. When it comes to finding the speed and the velocity, I'm going to cover both of them at the same time because they're found the same way using slightly different values. The most important part of calculating speed or velocity is realizing that on a position time graph, if I take any 2 points, we'll say this point and this point, along a line, I can find that the rise, which is measuring a change in position, and the run, which is measuring time, right? My change on the x is time, my change on the y is the change in position. So slope is rise over run. If I replace that with my variables, slope is delta x, which is displacement, and t, which is time. So you can see here that the slope of a position time graph gives you displacement over time. Hopefully, this is screaming out to you that if I find the slope of a displacement time graph, it will give me the velocity, right? The units for y are m, the units for x are s, or seconds, so meters per second, which also tells me that it's velocity. So please, we need to get used to this. Anytime you're given a position time graph, if you find the slope at any section, you will find the velocity of the object at that section. Just to give you an example, because I think the examples tend to make things more clear. This is a little cluttered. I'm going to explain. I've used different colors to hopefully differentiate between what I'm trying to say. I've included dotted green lines just so it's very clear what points these are located at. So here I have A, B, C, and D. I have 4 segments of the motion. So if I'm just looking at A, well, I go from 0 all the way up to 40. So my distance is 40. B, I don't go anywhere. I stay at 40. Yes, I've gone all the way to 40, but for the next 2 seconds, I don't do anything. I'm still at 40. So just for B, I don't go anywhere. My distance just for B is 0. I then go from 40 down to 10. My distance is 30. And finally, I go from 10 up to 30, so I go on a total distance of 20. If I add all of these up, my total distance for the whole thing will be 90 meters. After completing this motion, I will have gone 90 meters. Hopefully this makes sense based on the earlier descriptions of how to find distance. I'll now do the same thing, but in this case for displacement. Same concept, except now direction matters. So yes, I still went 40, but I have to say positive 40 because I went 40 away from where I started. I didn't go anywhere, so I don't have to worry about a direction for part B. It's still 0. Just for section B, that doesn't mean for section B, I haven't displaced anything from where I started, but from point B, from beginning to end, I don't experience any displacement during that time. For part C, I go from 40 down to 10, so yes, I experience a change of 30, but it's negative, 30 in the other direction, going back towards where I started. And finally, if I go from 10 to 30, I experience a displacement of positive 20 or 20 away from where I started. If I add all these up, you'll find that my total displacement was 30 meters away from where I started. I could have also just looked 0 at one end, 30 at the other, positive 30, 30 meters away. The time, if I look at A, well, it took 4 seconds to complete that motion. It took 2 seconds to go through the leg of motion that's represented by B. It took me 4 seconds to go through C, and it took me 4 seconds to go through D, for a total time of 14 seconds. So hopefully you're starting to see that I'm looking at each section individually, and I can also determine the total. Now, speed and velocity, this is where things don't necessarily get tricky, but you have to be very careful. Since speed is distance over time, I have to take my distance value, which is 40, my time value, which is 4, and distance over time, 40 divided by 4 is 10 meters per second. For this first section, I was traveling at 10 meters per second. B, well, 0 divided by 2 just gives me 0. I didn't have any speed. I didn't go anywhere. I wasn't moving. For C, my distance 30 divided by my time 4 would give me 7.5 meters per second. And lastly, D, I went 20 meters in 4 seconds for a speed of 5 meters per second. Now I can't simply add all these up because remember, with speeds and velocities, we can't just add them up. We can't just average them as if they were regular numbers, but we can use the totals that we found before. My total distance, which was 90, divided by my total time, 14, gives me 6.43 meters per second for the average. And if you look, you'll find that 6.43 generally falls within the range of these values, so it's a good average. But I can't simply just add these 3 up or these 4 up and divide by 4. That will give me the wrong answer. Finally, to find the velocity, same thing. If you understand how we found distance and displacement from this graph, it's just a matter of taking my displacement and dividing it by my time. So in this case, positive 40 divided by 4, which is the time, gives me positive 10 meters per second. 10 meters per second away from where I started. For part B, 0 divided by 2 is 0. For part C, negative 30 divided by 4 is negative 7.5 meters per second. I'm not going to continue to repeat the calculations, but hopefully you're seeing that the distance over the time gives me speed, displacement over time gives me velocity. Finally, again, I can't just average everything. I have to take my total displacement, which is 30, divided by my total time, and I'll find that my velocity was a positive 2.14 meters per second, which was 2.14 meters per second away from where I started. So I apologize, that was a lot of numbers, a lot of equations I threw at you. The main takeaway, if you can find the distance and the displacement, as explained in these previous sections, all you need to do at that point is read the times for whatever sections you're analyzing, and you can quite simply find the speed and the velocity. The difference is when you want to find the total or the average for the whole thing, you cannot just add these columns up and average them. You must look at the total distance or total displacement and the total time, just like we did in the calculation problems where we weren't using graphs. All right, so here's a practice example down here. I'll explain it, and then I'm going to leave this up. I would suggest you pause the video, and then I will talk about the solution to it after you guys wait about 10 seconds after you unpause, and the explanation will be there. So really quickly, you are given a position time graph with 1, 2, 3, 4, 5 different sections of motion. I've thrown in these dotted lines to make things very clear, and the 2 questions I'd like to know: what is the average speed for the entire trip, and what is the average velocity just from 0 to 14 seconds, ignoring this last leg? So give that a shot. I would suggest you pause the video now. Once you have your solution, you can unpause the video, see what the solution is, and double check your work. To look at the answers really quickly, the first one asks for the average speed for the entire trip. So speed is distance over time, and since it's the average speed for the entire trip, I need to know my total distance and my total time. The total time should be easy. The whole trip took 20 seconds, so 20 seconds is my time. The distance, I just have to add them up. I went 30, then I went from 30 to 70, which is 40, so I went 30, and then 40, then nothing. Then 70 down to 20 is 50, and then from 20 up to 40 is 20. So all I did was take those 30, 40, 0, 50, and 20. Direction doesn't matter. I added them all up. 140 divided by 20 gives me 7 meters per second. If I want to find the average velocity from 0 to 14, similar process. However, I only want the displacement. So in this case, my displacement was positive 30, followed by positive 40, 0, and negative 50. So if I find my total displacement, 30, 40, 0, negative 50, that's going to equal positive 20 meters or 20 meters away from where I started. I could have also simply looked at my starting and in this case my ending at 14 seconds time or location and know that I went from 0 to 20. I could also get positive 20 that way. In this case, we're only looking at 14 seconds of time. 20 meters away from where I started divided by 14 seconds gives me 1.43 meters per second away from where I started.